Hello friends, welcome back again. In the previous videos we have completed the fluid static parts. Now moving on, another section of the fluid mechanics is fluid kinematics. So the fluid kinematics is the branch of mechanics that deals with the fluid of motion. That means in the fluid static part we have studied the fluid at rest. Now we are moving to the section where we study about the fluid in motion. So a fluid kinematics, it is a branch of fluid mechanics that deals with the fluid in motion without, this is the important thing, without considering the forces due to which the motion develops. So here we will not focus on the forces parts, we will only study the flows. Okay, here the flow properties, the flow conditions like velocity, acceleration, pressure or density, these are the function of space coordinates and time. So this is velocity, acceleration, it is a function of space coordinates x, y, z and time. So now in 12th class you have already studied about the this approach where we have to deal with the a body, like when we talk about a collision is occurring between two bodies. So we have to see for this analysis we take consideration of the body of a body and we analysis what is the velocity, what is the acceleration of a body which is going to be collide with another body. So what we used to do, we study a single body part in the mechanics. But if we talk about in terms of fluid mechanics, in fluid there are various numbers of fluid particles. So here the individual study of every particle is very difficult. So this type of approach where we focus on one single particle, one single body, this approach is known as Lagrangian approach. Here the behavior of individual fluid particle is studied. That means the velocity, acceleration, the other flow conditions of a single particle is studied in this approach. But it is very difficult because there are billions of fluid particles in a fluid mass. So here, to avoid this, we have another approach that is known as Eulerian approach. So in Eulerian approach, we study a control volume. Here, a control volume is taken in a fluid. The variation of properties of fluid flow like velocity, change in velocity, change in acceleration, density and pressure, these kind of changes we will study by taking a control volume. So what are the changes that occur in this control volume? This is a fixed volume. What are the changes, what are the inflow of mass, what are the outflow of mass occurs at that section is studied. This approach is known as Eulerian approach. So in fluid mechanics, we will follow the Eulerian approach because it is convenient to study. So now moving on. So there are various types of flows. So depending upon the fluid properties or the properties of flow. So what are the fluid exactly? On the property of fluid that governs the flow, that describes the two types of the category. One is ideal and real flow and another is incompressible and compressible flow. And when the flow is depending upon the properties of flow, which is laminar and turbulent, and second one the steady and unsteady, uniform and non-uniform, rotational and irrotational. These are the category of flows. These are the types of flows which depends on the flow properties, and this one are the types of flows which depends on fluid properties. So we will study briefly about these types of flows. So first of all, the real and ideal and real flow. So everyone know what is ideal fluid? I have already told in the previous videos. Ideal fluid is a fluid where the viscosity is absent. the viscosity is 0. Here the viscosity is 0, and the real fluid is having some viscosity. Okay, so ideal fluid is a hypothetical fluid. There is no fluid is there is no fluid available which behave as an ideal fluid, but for the convenience of study, we assume ideal fluid. Okay, so a real fluid is a flow of real fluid implies viscosity, and we have known viscosity by the Newton's law of viscosity. Here viscosity is nothing, it is the resistance offered by a layer of fluid to the another layer. So a friction effect is developed, and due to the viscosity, the friction effect is developed, and hence the frictional losses is there. So in the real part, you can see from the diagrams, it is ideal flow, it is a real fluid flow. Here the friction is available, and the energy loss will be there because due to the friction losses. But in ideal flow, which is a hypothetical fluid, which is not a real fluid, assumes no viscosity and no friction losses. So here there is no losses, no friction losses, no energy loss here, and the velocity profile is linear. Sorry, the velocity profile is uniform, and here the velocity profile is varying as we go across the flow. The velocity of the fluid varying. Here the velocity is near to the boundary, the velocity is low due to the frictional force offered by the surface. Because this surface is at rest. This surface is at rest. Fluid is flowing. The resistance offered by this layer to the another layer, and by this layer to another layer, and hence so on. So this is how the resistance, the friction force offered by a layer of fluid to the another layer of fluid. So that's why the velocity gradient developed. So now moving on, the another type is compressible and incompressible flows. So everyone knows the compressible and incompressible fluid. The density is constant. If we talk about the incompressible fluid, the density is constant. That means density is not varying. But in case of compressible, density may increase or decrease. But here we are talking about the flow. Okay, first of all, fluid is considered to be incompressible fluid. Liquid is considered to be incompressible fluid, and air is compressible. But if we talk about the flows, for liquid, which is assumed to be incompressible, the flow will be incompressible in nature. But for gases, because gases are assumed to be compressible, here the flow may be compressible or may be incompressible depending upon the variation of this density. So if we talk about in terms of density variation, if the density variation in the flow is less than 5%, that flow is considered to be incompressible, and if the density variation is more than 5%, the flow is known as compressible flows. So this is the general criteria of describing or distinguishing the flow on the basis of compressible or incompressible flow. So now moving on, there are two types of flows now, laminar and turbulent flow. So laminar is nothing when a fluid layer is sliding smoothly over another fluid layer, is known as laminar flow. That is simple definition. When fluid flowing in sheets of laminas is smoothly sliding over one another. Here you can see it is in the diagram. It is a layer of fluid flowing, and it is another layer of fluid flowing. It flows smoothly over one another. There is no mixing available in the fluid. There is no mixing available in the layers. That means no molecules of fluid, no element of fluid will transfer from one layer to another layer. There is smooth sliding. Okay. So generally laminar flow occurs at low velocity, and here no macroscopic mixing is available. That means mixing means the mixing of fluid element from one layer to another layer. But if we talk about the turbulent flow, it is a highly disordered flow, disorganized flow at higher velocities. So at higher velocities, turbulent flow is turbulent flow is dominate. And also here the macroscopic mixing of fluid elements, fluid particles available. You can see from the diagram, there is no fixed pattern. Just like in laminar flow, there is no fixed pattern. It is a random flow. It is a random flow. The fluid element, the fluid layers, the laminas are intermixing between each other, and fluid particles can be shifted from this layer to that layer and this layer to that layer. So it is a highly disordered, disorganized flow. So the second type of flow we can categorize as steady and unsteady flow. Steady means the property which doesn't change with time. Okay, steady is the property which doesn't change with time. And unsteady means where the flow conditions change with respect to time. So here the properties which remains with respect to time. It means if we talk about the velocity, if the velocity is not changing, not varying with respect to time, it is known as steady flow. That may be, or maybe the acceleration, the pressure, the density, any property, any fluid property which is not changing with respect to time is known as steady flow. Taking an example, say there it is a nozzle. Here the velocity is 5 meter per second. Here the velocity is 10 meter per second, and again here the velocity is 7 meter per second. It is a just general condition, flow condition. It is given at time t1. And again, if we talk about, if we say at time t2, here let me just make it here. If we say just time t2, the same location, again the velocity is 5 again, here the velocity is 10, here the velocity is 7 again. That means time has been changed but the velocity doesn't. This type of condition, this type of flow is known as steady flow. Okay, here the velocity may vary, velocity magnitude may vary as it go from one section to another, but it will not change with respect to time. So and instead, if the flow condition changes, suppose at time t2, if it will become 15, it will become 20, and it will become, say again 11, say some examples. So the condition has been changed, the velocity condition has been changed now at some different time. So this kind of flow is known as unsteady flow. Okay, so and moving on, the another type of flow is uniform and non-uniform flow. First we have learned the steady and unsteady flow, where the velocity variation depends upon time, where the time velocity is not the flow condition is not varying with time. That means steady flow. Here we are talking in terms of space, where the fluid properties doesn't vary, flow condition doesn't vary with space, is known as uniform flow. And if it varies, it's known as non-uniform flow. Say taking one example, it is a uniform duct. Here, if the velocity at this point is 5 meter per second, and here the velocity is 5 meter per second, and here again 5 meter per second. Here we can say it is a uniform duct having uniform cross section. The velocity which were earlier at 5 meter per second, now it will again at some another location 5 meter per second, and if it move again to at some another location, it will remain same 5 meter per second. So here the velocity is not changing with respect to the space coordinates. So this type of flow is known as uniform. Here the properties can be velocity, acceleration, density, etc. And if it will change, taking the earlier example, if it will change, here 5 meter per second, here as the 10 meter per second. So this is the change in velocity with respect to space. So this type of flow is known as non-uniform. Okay. So these are the flow combinations. I told you earlier, and let's just say let's look again one by one. Steady uniform flow. Steady uniform flow means a flow which the flow condition is not depend on time, and the flow condition again not depend on space is known as steady uniform flow. The flow at constant rate through a duct of uniform cross section. Flow at constant rate through a duct of uniform cross section here. Here, say 5 meter per second here, again 5 meter per second here, and 5 meter per second here. Here the velocity is not changing with respect to the location. Say time t1 is given, at time t2 the same condition we get again 5 meter per second. So this type of flow is known as steady, because it is steady, doesn't vary with time, and uniform, doesn't vary with location. And moving on, another second is the steady non-uniform flow. It is again steady, doesn't vary with time, but it is varying with space. That means non-uniform flow. The flow at constant rate is constant. That means the rate is not changing with time through a duct of non-uniform cross section. So here the duct is at non-uniform cross section. So duct is non-uniform cross section. Here say velocity will be increasing. If we go here, if it is 5 meter per second here, it may be 10 meter per second here. Okay. And if this condition isn't varying with time, again it means it is steady, but obviously it is not uniform. So it is a condition of steady non-uniform flow. So now talking about the unsteady uniform flow. Here in both the conditions, this is unsteady. Unsteady again, flow condition changes with time and uniform is given. That means section flow doesn't depending on the location. So if we talk about here, say unsteady, say just take an example here. It is a one flow condition, it is another flow condition. The cross section is same, flow at varying rate through a duct of uniform cross section. Here say it is the velocity at 5 meter per second, uniform cross section is given. Again velocity is 5 meter per second. Here again velocity is 5 meter per second. But this is the given, say at time t1. Now if we talk about the time t2, the velocity is now maybe increase, say 6 meter per second. Here 6 meter per second, 6 meter per second. So we can say that it is here the velocity is same everywhere, but at time 2 the velocity is different but uniform everywhere. So this is the condition of steady non-uniform flow. So unsteady uniform flow. So in unsteady non-uniform flow, here the velocity condition also varying with respect to space. So this is a condition when flow at varying at rates through a duct of non-uniform cross section. Okay. So another type of flows we can be categorized as 1D, 2D and 3D. Okay. If the flow conditions, we know that velocity, the flow condition is depends upon space coordinates and time. So here if the variation of flow condition is in three different, we have the three different uniform coordinate of axis, that is x, y, z. So if the variation of the condition is along x, y and as well as z. So if the condition is varying in all three space coordinates and obviously time also, so this type of flow is known as 3D flow. And if we talk about 2D flow, the flow condition is just varying in two space coordinates. Say it may be vary in x or y along with time, it may be vary in y or z along with time. So this is type of the 2D flow. And 1D flow, here the space coordinate is the condition is varying at one space coordinate. So velocity may be a function of one space coordinate, maybe x, maybe y, or maybe z along with the time. So these are the three types of flow: 1D, 2D and 3D flow. Now moving on, talking about some rotational and irrotational flow. Rotational flow means a rotation of a fluid element at its location. When a fluid particle rotates about its center of mass, that is, say it is some flow. Here the fluid element, if it is rotating about its center of mass and moving along to the flow, so this type of flow is known as rotational flow. And if this, say this is a element, if it is not rotating about its center of mass and just keep on moving into the flow, along with the flow, this type is known as irrotational flow. So force vortex is an example of rotational flow, where we can example say flow of water in an impeller. Flow of water in an impeller. Here we can, if you are going to analysis, you can find the fluid element. You can find the fluid element will move along to the flow, and as well as it will rotate. Okay, it will rotate just like here. And whirlpool, in a way, you have seen a whirlpool has been, a vortex has been generated in a wash basin. So this is an example of irrotational flow. It is a free vortex flow. Here you have seen in a wash basin, just like it. If some element is there, it will again sit raised here and again raised here. So it is a rotational flow. The flow is rotational, but the fluid element at its location is not rotating. So the condition of rotation should be fluid element should rotate at its center of mass. Okay, so this is a case of irrotational flow. So these are the types of flow we are discussed. Now just taken some examples from the previous year gate. Here it is asking a flow field which has convective acceleration is. So we will talk about it, but just take an example. Convective acceleration. Acceleration in the coming slide we will discuss about the acceleration of fluid elements. So acceleration can be a function of space coordinates and time. It can be a function of space coordinate and time. So the convective acceleration is when it depends on space coordinate, when the acceleration is varying at space coordinate as per the space coordinates. So here it is given only convective acceleration. It means it is not depend on time. So what will the condition of flow? So when it is not depending on time, the condition will be steady. So here the condition will be steady, but it is varying with space, so it will become unsteady. Non-uniform. So steady non-uniform flow. So option C is correct. Here, for an incompressible flow field V, which of the following condition must be satisfied? So the flow condition, these are the equations. Let's say for an incompressible flow field V, which of the following conditions satisfied? Incompressible flow field. So incompressible flow field is defined by del dot V. It is an equation of continuity. It is a continuity equation. We will going to discuss in the coming slide. It is a continuity equation. Okay. So option C is correct. And this is a question asked in the GATE examination. For a fluid element in a two-dimensional flow field, if it will undergo a fluid element in a two-dimensional flow, say x and y coordinate, it will undergo what kind of motion? It can translate here to here, or here to here, or it can rotate. It can rotate in any direction. So rotation, or it can also say taken a fluid element it can also deform as the shear due to the viscosity of the fluid. So it can be deformed. So there may be any condition. It may be translation or deformation. It is not necessary to have only translation or only deformation condition. So it may be translation or deformation. So this is all about the fluid types of flows we have discussed in this video. In the next video, we will talk about the other terms that include in the fluid kinematics. So thank you.